Hello, that's Michael. I'm going to show you how to use the QMLMaterial for a simple problem. So the first step is once you have the executables of the QMLMaterial software, you have to provide the path. So the Python path is just the place where the QMLMaterial is. In this case, you have the folder workspace in your home with QMLMaterial 3.5 and the QMLMaterial folder where the code or the executables are. By doing so, you are able to run the QMLMaterial. So here is the folder where we have everything to run. But first, let me show you the problem that we have at hand. So let's try to visualize the problem, the chemical problem. So in this case here, we have a cage which is silicon 11, and we wish to dope that with aluminum. And the question is, which is, for this doping problem, by having free aluminum in this cage structure, the question is which distribution of aluminiums is the optimum one. I mean, the global solution or the global minima or the putative global minima solution. It's a discrete search, and we are going to solve this problem by using active learning, by using Gaussian process, specifically the regression, as implemented in the QMLMaterial. But not just that. We wish also to find the optimum spin multiplicity. So we are going to search for the optimum structure plus the optimum spin multiplicity. Okay, so in order to run the QMLMaterial, given the problem that I showed you, we have to have here the files, all computed configurations. It is for benchmarking, which is this example, but this is where all calculations of all isomers or homotopes are present, right? So we have the configurations of doping and the multiplicity computed by DFT using the demo 2K. Those energies are in Hartree. So in this example, we have a benchmark which is also implemented in the QMLMaterial. This is just for a tutorial purpose, but of course we can use the QMLMaterial iteratively by calling some calculators like demo2k and Quantum Espresso, DFTB Plus, etc. But in this case, we have to have this file with all possible spin multiplicities and structures, which defines our search space, which is 495. Okay, so we have some readme where I just show which one is the putative global minima in the energy in Hartree obtained from DFT, and the GM in the scaled energy, which is this value here, and this value here is the one that we are going to search using the active learning in the QMLMaterial. Okay, so we need all computations, the input, which is MLMaterial. We need an initial database with, let's say, 20 initial structures. Okay, your initial population. And you need the reference where is the cage, where we have silicon 11, which is going to be doped by aluminum. So we need just this 1, 2, 3, and 4 files. So here we have the input of the QMLMaterial. So here we have, for example, the keyword for the absorption on surface, cluster on solid, and the dictionary in Python for atomic cluster using genetic algorithm for sampling. And in this case, we have a defect. So aluminum doping silicon. That's the flag that we are going to concentrate, but those are related to all the features in the QML material. Alright, so in the beginning we need the name of where the cage structure, the reference structure is. So this one we keep empty. This flag here is which atom is to be doped or modified. And this one here is the dopant, which in this case aluminum. And the index of the silicon atoms that are the index that shows the index list, which shows the atoms that are going to be doped. In this case, the 11 atoms that we have in the structure. So here we need, for the descriptor of the electronic part, the spin multiplicity that we are going to search together with the doping structures, 2, 4, and 6 the multiplicity, and we need this additional vector for the duplet, so spin multiplicity 2, and here we have the spin for 1 electron, and here the last one is the number of unpaired electron. So we do the same for the quartet. The multiplicity 4, we have 3 unpaired electrons, and the total number of spin for these 3 unpaired electrons. And the same for the multiplicity 6, 5 unpaired electrons, and the total spin multiplicity 2.5. So here we define the spin multiplicity data. We have the system, which is a molecular cluster, atomic cluster. I mean, we have a molecule. Or if we have, for example, a surface or a nanotube, and we wish to do this kind of study using a periodic boundary condition, we need just to set up this flag, which is not this case. So that is the input part 1, and here we have the input part 2, which is specifically for the active learning. So in terms of the machine learning, we have the test size. So in this case, this is 5%. As we are using Gaussian process, the uncertainty is obtained from the method. We don't use resampling like k-fold cross-validation. Therefore, we have this splitting flag for bootstrapping or k-fold cross-validation. But these flags are not going to be used because we are using Gaussian process. So we have the debug false, the number of jobs, so for parallelization, but it's not, I think, implemented. And I mean, this is for the scikit-learn regression. So if we put -1, we can use all the threads. But never mind in this case here. So as we are going to scale the total energy to have a better regression model, we change the global search or the search from active learning from a minimization to a maximization. So that's why we put is max true. Okay, now we have the active learning flow controller. So we have the number of iteration steps. So in each step, we are going to ask the agent or the expected improvement acquisition function to select the 5 structures and the spin or the spin multiplicity that is going to be computed in order to find the optimal solution with fewer steps as possible. So the number of iterations, the total 21. So in each one of these iterations, the agent will ask for 5 new calculations, or in this case, as we have this benchmark, is I/O. The initial data size, which is 20, which is in this file here, regression data 20. And the optimization model, efficient global optimization, or we can do this randomly for benchmarking. So the acquisition function for the ego is the expected improvement. We can use lower confidence bound or upper confidence bound, which is not the case. We have other acquisition function, exploitation, pure exploration, and here we have the descriptors. So for example, we have the Coulomb matrix and the MBTR, which is the one that we are going to use. The number of atoms to be doped or removed, 3, because we have 3 dopants, which is the aluminum. So we have a benchmark, so we put is possible random configuration false, and we have the path where this job is present, and the printing level, which is minimum. Here we do the scaling of the energy. So what we do is to get the total energy and subtract by this value and divide by 100. And we have the plot range, because in each iteration we have the plot of the quality of the regression, and here finally we have the scikit-learn for the Gaussian process with the kernels. So we are ready to run the QML material for this simple example. So we just do this, and we can see some progress. So we do like, let's see if it is running. Okay, it started. So we do grep var the output, which is loop 1, and we can see the maximization of the objective function, which is the total energy in a scale form, right? So we do that, the iteration starts, we have the output, so the QML material version 3.5, some papers that we quote or cite, and some information. And the minimization or maximization is in this flag. So maximum observed so far or minimum. So we have also as output the regression in each step, the step 7 for example. So here we have the training and the testing, the red one. So it's plot during each active learning cycle in QMLMaterial. So let's see. Okay, all right. We found the putative global minima, or the global minima, because it's a discrete search and we know the optimal solution. So this is the optimal solution, the global minima, which is the configuration of dopants in the cage of Si11 6, 7, 8 with multiplicity 2. Remember that we have the multiplicity also 4 and the 6, that is also in the search. The energy in Hartree is this one, and in the scale energy is this one, which is this. So once we have the scale energy, to get the energy, the actual one from the demo, which is present here, we just do this value here, which is present here, the energy scaled value, and the scale division. So we do that minus the total value scaled divided by 100. So let's see. Okay, yes, that's it. So that is the energy, which is the referred to the global minima. So we could find in just few iterations the optimal solution. Let's see the plot when we have around 100 data, because in each step we have 5 structures with their spin multiplicity that are asked to be computed in each cycle. So we have around 110 structures. Let's see in this plot. So we have here, we have the Gaussian process, the alpha hyperparameter from the Gaussian process, the mean absolute error, and from the training, and here for the testing. And in the descriptor we have the structure using the MBTR descriptor as implemented in the describe library plus the spin multiplicity. So that's it. That's a short tutorial about how to use the QML material.